glad to see all of you here, and thank you for the hospitality of Hong Kong University, which is used to be my my undergraduate. Well, I spent a lot of undergraduate years right here, and now I turns out to be an other colleague there in the rivalry there in Chinese U. Now, basically, I would claim myself as a pedestrian in this area, as a data analytics or something like. Well, I'm coming with the background from financial mathematics, applied mathematics, dealing with PDE, and together with the traditional statistical methodologies. But what I'm going to tell you right here is that's why, well, rather than showing so many fancy pictures just like other experts did so far, I would more or less convey a philosophical message and also a kind of numerical scheme that would be pretty useful for the deep learning in general, right? So basically, I will tell you one by one. And first of all, just get back to something very simple, okay? Everyone should know. As a kind of machine learning, okay, everyone should know that it's just a kind of static and dynamic optimizations. Well, to me, at least it is the case. But of course, it contains much more fun, right? Just like depending on the data structures, we should have to refine it a little bit different. And of course, we were looking for a model-free framework, okay? And most of the time, we are facing a huge amount of data, and most of the data will be categorical as well as continuum, and they are mixing together as well, okay? And apart from that, the algorithms would mostly robust. This is something that we would like to aim for. But turns out at the end, most of the machine learning algorithm is quite sensitive to the data. And also, well, just like all the other experts, they would prefer to introduce something very simple algorithms, dealing with the big data at the same time, and provided that we have a large computing facilities, okay? And we found wild applications in image processing as well as speech recognitions, okay? But it turns out to the stage that apparently, not sure whether mathematics could still be of use, right? Many students would say, well, even professors would say, I would say, even many colleagues of mine coming from computer science background, they would claim that, come on, should we still learn calculus or mathematics in general? Well, at least right here I would say yes. Okay, particularly for the intelligent, dynamically controlled system, I would think so. I would think so. So, at the very beginning of my talk today, I would like to, well, remind you what is the basic heuristic component of supervised learning. Okay, of supervised learning here. And then we gear up to deep learning. Everyone should know what it is. Okay, just the different layers of networks. But it turns out that we can view the deep learning as an optimal control problem from a recent work up here in JMLR, okay, machine learning research. And I will share with you. And turns out at the end, we can now boil down to, well, quite a general class of deep learning problem into control theory problem in which we can use a very, well, we propose basically a very general method called the control boosting algorithm that finding out the optimal control, or henceforth finding out the weights appear in the deep learning algorithms. Okay, so this is my purpose today. Okay, so everyone should know, and quite a number of speakers already raised these issues. Just undergraduate, even right now, it turns to a high school exercise to tell them the supervised learning is something that you have the data, X, which is the inputs, and you have some labeled data. You would like to match them through along parametric functions. And the standard is pretty, well, the calculations or the objective functions is rather standard. In a sense, we would like to minimize this kind of objective functions whenever we would like to fit it with a non-parametric functions. Okay, we would try to find as regular as possible for that functions. That's why we have the additional Lagrangian. And while for the parametric method, we would fit it with a number of basic functions, and we would like to fit with the coefficients. And the Lagrangian condition here is telling us we try to reduce as many basic functions as possible. Okay, so roughly speaking, these are the functions behind. And in general, well, at the very beginning, day back to 1960, we already have the ANN, Artificial Neural Network. And what they derive is in this way. It's a rather shallow neural network. In a sense, we only got several inputs, okay? Just one hidden layer, okay? And we have the transfer function or iteration function, okay? On which we just try to boost, okay, the linear combinations of the inputs, and turns out that to some other outputs, okay? So roughly speaking, this is the structure. And the main framework for this is we have something very universal. The linear combinations involved it, and together with the iteration functions. Sometimes you just choose the logistic function, indeed, okay? And, well, apparently, this is the neural network, okay? The how to get it further and proceed further, and it turns out we have the deep learning, okay? Deep learning, of course, is a more sophisticated neural network in the sense that all the weights can be calculated in a recursive manner, which is pretty convenient, okay, in a convenient manner, okay. And it's just like with the shallow neural network, they share with something common in the sense they have output functions right here, which is a composition of the iteration functions together with the linear combinations. So this component is pretty standard, right? And also we can have certain recursive relations to calculate rates. But from this point of view, we can observe something very generic. At least we can rewrite our output in terms of a discrete dynamics, okay? We have, well, we can regard K here, that means different layer, right? Regarding them as different hidden layers, and we can regard them as the evolution of time, right? And now right here we have our F bar here, okay, which is something universal, just the composition of the iteration functions together with the linear combination functions, okay? And we have different ways and intercepts as well, okay? And then let the neural network evolve over different layers, just like evolve across the time. Okay, so this is the view. And indeed, there is a work appeared recently by Wei and Yi, there in Princeton, in JMLR, Machine Learning Research, just this year, okay? They teach us that, well, we can actually reformulate all the deep learning problem in the optimal control problem in this sense. For the discrete time setting, okay, we can rewrite it as by rewriting our original F bar, the iteration function together with the linear combinations, okay, combining together, and then subtracting the identity functions, right? And in that regard, we can see the change or the increment of the outputs, okay? Where the F here is now standing for something universal, okay? Which is the common point that can found in deep neural network, okay? Deep learning, okay? But we can also generalize in this manner to a more push to the limit, okay? If we have more and more hidden layers, right, the times we're getting closer and closer, just like the concepts which is pretty prevalent nowadays, mean field games, and I suppose I'm one of the active players over there in that area as well. We can push to the limit to find the approximate controls, and that controls theta t, well, the weights I would say. The theta, that means originally our weight W and together with the intercept B can now be regarded as the control, okay? As the control, theta. All right, so in this sense, for very complicated and large neural network, we can just push it to the limit and consider it as a continuous time dynamical system. And by that time, T is just standing for the layer, the order, the numbering of the layers. And then we can have the universal function F, which is the composition of the iteration function together with the linear combination, as I said. And all together, we only have to solve for this dynamical systems. Okay? Theta T is the control in the dynamical system sense, in the optimal control theory sense. And now it turns out it is the weights in the deep neural network. And this guy, just the evolution of the outputs, okay? And at the very far end, X capital T, that means the expiry date, that time. That would be our approximations of the ultimate outputs, okay? Given the initial, that means the input, okay? It will evolve to the end to get the output at the far end, big T. So in this regard, we reformulate all the deep learning problems into our optimal control theory problems, okay? And of course, we can try to regularize them, okay, try to reduce the number of layers, and also try to make it more smoother in the sense we add penalty functions, just like before for the supervised learning. For the supervised learning, right here I mentioned before, we have the Lagrangian here, okay. For non-parametric case as well as for the parametric case, we try to reduce our model as much as possible, right? And we're doing the same as well. We have the penalty function. Sorry, I think I couldn't manage this quite well. I better use the old school fraction. Now, right here, so you can see we have the, hold on. Now, so we have the penalty functions and try to make the output or the control or the weights to be more regularized. So in general, this is the optimal control problem. And from now on, we can just focus on solving these optimal control problems. But this time, we can use back some machine learning techniques. And particularly, we can borrow the philosophy coming from the gradient boosting. That's why our algorithm is called control boosting algorithm. Now, how about, well, in general, this is the way we can solve. Well, we can actually face with two principles to solve our optimal control problem. One is the dynamic programming principle, and the other one is the maximum principle. And for the maximum principle, we can rewrite what we have there before. F is just the activation functions, right? That part. And we can propose an adjoint process, okay? And altogether, both these two guys, this is a forward evolution, something that we would like to build. And this guy is the backwork. We would like to solve it, which is auxiliary. We can use it to solve for x and also solve for the theta hat. That means the weights and the intercepts, okay? And of course, we would like to find out theta t, and how to find it out. It is just minimizing the Hamiltonians, okay? The Hamiltonians composed with two parts. One is the activation function right here. Okay, activation function right here, together with the L, which is the penalty functions for the regularity of the parameters or the weights. Okay. Okay, so well, one of the very old school approach is just looking for the fixed point. But everyone should know looking for the fixed point will be pretty slow. Okay, even, well, I would say, maybe you would say just like k-mean clustering or something algorithm. Looking for the fixed point most of the time, it will be time consuming, especially if x is pretty huge amount. Okay, that would be a problem. So that's why it's better for us to try to transform the problems back to PDE, and then using some machine learning or even the other way around deep learning problem to solve for that PDE for us. So this is my purpose later on today. Okay. Anyway, so solving for this fixed point is not quite, I would say, too tedious, okay? But anyway, from their work, okay, from Wade and Yee's work, they tell us that there could be some improvement, but at that time, they still use the maximum principle. Something similar right here, but with some modifications to resolve the matter. That's why it comes to our own contribution, okay? Right now, we try to tidy up the terms, okay, and try to keep the notation as like before, but try to make it more generic, okay? G is now our activation function, F, right? And A is our control parameter, theta, okay? It will be more generic right now. And for payoff function, it's more generic as well, okay? We put in this way, okay? With a discount factor that makes the problem more stable, okay? So, we would like to find a solution, or particularly solving the optimal control, or in other words, the optimal weights for our deep neural network. Okay, how to solve that guy out? Well, as I said, one of the ways is using the maximum principle, but there are some other prevalent tools. Okay, some other prevalent tools. Just like with our my collaborator Spencer Song, he's actually used to be the director of INRIA before. Okay, and he proposed maybe we can use the Bellman equations, okay, rather than using the maximum principle, we use the dynamic programming principle, okay, and we can solve it recursively, okay, but we can see the optimal control A right here somehow is related to the differential of U Okay, U is the value functions. That means our original optimal values of the target functions, right? Something objective function you would like aims to minimize it. And at that time, dealing with the differentials, we may face a hurdle. It could be too sensitive to the data and is highly non-robust. That's why sometimes we come with the ideas of using gradient boosting to try to linearize that thing, okay? And right here, we know A, of course, we can use the HJ equation, okay, the Bellman equations, sorry, HB equations, Hamilton-Bellman equations to solve for the U, and then running backwards, and once again, we have a fixed point. But as I said, this method is not so robust because of the presence of the differential. Okay, so we got a trouble here. And also this du could be quite, complicated in the sense that it is high dimensional and they are coupled with one another. Okay, so we face a hurdle right here. And some other methods like Powell, okay, Powell, they also propose by using the backward induction, okay, solving the dynamic programming principle running from the backwards to the very beginning. And of course, together with Wade and Yi and some other scholars, okay, even day back to the old days, they use the maximum principle. Okay, what is exactly what I just introduced to you. So, apparently, all these methods have their own limitations as well as the advantage. Okay, and thus, well, anyway, we may try to refine. Well, as far as we can see, the maximum principle may not be so promising. We have so many iterations over there. Perhaps we can try to boost the approximates better by taking care of this differential. Okay, so why don't we try to differentiate all of them together? Well, at the end of the day, A should satisfy the gradient of this function and try to equate that function, the gradient of that function, with 0, right? Why don't we try to use that equations? Why don't we try to use the Hamiltonian Bellman equations right away? Okay, it turns out that it is plausible to do. Okay, what we do, here is the reformulations that I just indicate right there. Okay, U is something that we would like to look for, and it is auxiliary functions, the value functions. And A can be found out by using this, optimizing this guy. Okay, but with the presence of the U, the problem will be too sensitive to the data. So what can we do? Why do we just try to treat this guy du as a single object? Okay, it's something that we would like to solve for directly. Okay, and by that time we consider it to be lambda. And by calculus trick now, okay, we can actually have differentiating x on both sides, okay, both sides of the Bellman equation, okay, and by that time what we got is this guy, okay, alpha lambda, d lambda, okay, and all the rest, okay. Now, G and F is presumably they're given objects, so it's not a big deal for us. Now, we have lambda here. Well, perhaps you will say we still have the d lambda. But unlike to what we have before, all these differential equations becomes decoupled. If we can replace something A here, or this linear object lambda on the right-hand side, with the, well, previous, approximate points. Okay, by that time, all the differential equations would be uncoupled. Okay, would be uncoupled. That is the key. Okay, and it turns out that we can propose this is the, well, just like as before, we have something fixed point, but this time can be solved more effectively. Okay, and we let lambda k plus 1 and d lambda k plus 1 right here on the left hand side. But all the rest involving G and F, those known, we would just use something, put it here, okay, fit in it, lambda k, and then we can solve for this system quite conveniently because all the equations here, even though they are still PDE, linear type, okay, because we are dealing with the deterministic control rather than the diffusion control. And that's why we only got a first order differential equations here, but they are decoupled. Okay, all the differential term d lambda right here on the left-hand side, they are decoupled. Only coupling thing is on the right-hand side, but they are the input. So that would not be a big deal. Okay? And how about to find out the A for this guy? Okay, we can do the same as before. In a sense, we have now lambda k plus 1, which is getting out from these differential equations. So right now, it is not depending on the data so sensitively. Okay, it will be more robust by that time. And now we can have the, well, looking for the minimizers of this guy. Okay, and we can use kernel method or even parametric approach. We can do for where we can find our appropriate candidate A. Okay, even though we may not be able to find the ultimate optimum point, but we can still find a kind of suboptimal point depending on the kernel basics we are going to choose. All right, so why it is boosting? Okay, now perhaps finding for AK plus 1 right here, as I said, we can use the kernel methods, but may not be enhanced enough, and perhaps it's better for us to enhance the method, and that's why we have the boosted term right here. Okay, and this is the control, that's why we have the name of control boosting algorithm. And this AK here is the learning rate. Of course, it depends on the X. We are solving for the continuum of functions, so this learning rate rho K, it depends on X. But we still have a very simple algorithm, as I'm going to show to you. Okay, right here, it is the algorithm. Okay, first of all, we solve for the differential equations. They are decoupled, provided that we have the lambda k plugging in. It is decoupled. Okay, and by that time, we have different solvers, and we can use even using the deep learning to solve it back. Let's say the TensorFlow, okay, to solve this guy back. Okay, and how to get the next control? We boost that control, okay, by refining the term, as I just showed right here. Okay, as I just showed right here, rho k. All right, and then this learning rate is chosen in between these two guys. Of course, we prefer to choose the largest possible one so that our learning could be getting bigger and bigger. Well, presumably this guy, we need not to bother about the lower bound in principle, but with this lower bound, it will help us to have a more effective convergence. Okay, so this is the boosted control. Okay, it's boosted by refining this control with the gradient of the Hamiltonians. Okay. So that's why this is the algorithm, but turns out at the end, we still have to look for its effectiveness, whether it is whether this proposed scheme, first of all, whether it's convergence. Well, I think it's running out of time, so I better not tell the details, but just let you know for most of the canonical, almost close to the linear quadratic setting of our optimal control problem, this kind of algorithm is effective, okay? It's convergence at the end, okay? So we have certain lemmas. I skip all of them. And the main theorem is the convergence, I better say, is in a sense of the Sobolev norm, okay? Sobolev, in a sense, we put some weight here, okay? And also we have to deal with the differential of lambda as well. But, well, anyway, we just focus on lambda right here, but we can also talk about the differentials as well. And they are weighted norm, okay? We try to compactify the overall domain because we are dealing with the optimal control problem over the whole real line. Okay, so here is the convergence result. Now, turns out I got one graph for you to see whether this method is effective or not. At least for linear quadratic case, okay, linear quadratic case, something that you already got the closed form. Okay, you can compare with our convergence schemes. It turns out that, well, it's still acceptable. Just, well, 1 or 100 something iterations. Okay, it's just instantly it can get the answers. But the most important thing I would like to convey the message here in this talk is, most of the time, the input X, we are facing with a very, very high dimensional data. Okay, that means we have quite a lot of input variables, okay, more than thousands of them, okay. Whenever we are dealing with these questions, can we get a better off right here in this setting? I would say yes, in a sense. At least, as I said, as a conveyed, all the lambda here, okay, satisfy a decoupled partial differential equations, okay, and they are of first order, all right. Provided that they are decoupled, well, we can just solve by them with parallel computing, okay. And on the other hand, perhaps you would say this kind of differential equations, perhaps you already encountered quite a lot over these few days. You found the Lagrangian setting, you found the Lagrangian equations, okay, subject to different boundary conditions. Most of the time, the boundary conditions will be set to 0, okay, vanishing at the boundary, so that your equations can be solved quite effectively. But right now, we are not. We are facing something in optimal control theory problem. Most of the time, the boundary is not so trivial, okay? We should have to do something else to find a boundary. And the boundary, it turns out that because of this very special setting, is connected to the Jacobian flow, okay, of our original dynamics. It should be capital X, sorry. It should be capital X. The gradient x here is the input variable, okay? And we would like to find out the Jacobian flow. That means the sensitivity of our variable x with respect to the initial state, okay? And this is the dynamics that we can found, and they can be expressed explicitly simulate in the sense that all of these g here, they are pretty explicit, okay? We can found them as they are given. And it turns out that to find the boundary conditions, okay, it's just solve for this kind of representations. And once again, to compute this guy is pretty standard, okay. That's why our algorithm also fits well with the high dimensional data, okay. So I'm afraid, I suppose this contains quite a lot of theoretical stuff. At the end of the day, we still have to see whether this program can only be persuasive, provided that it fits well with the very, very high dimensional data. So I will allow such empirical experiments in the future talks. Okay, so that's all. I will just keep right here. Okay, thank you.
Thank you. Wait, can I just follow up on that point? Like, does it work?
Well, at least for the linear quadratic thing, it works. I always face this kind of problem, especially dealing with the PDE stuff. At least for the PDE stuff, I think it's work. Yeah, that's why I showed you for the linear quadratic case. Yeah, but of course you would say whether we can try to have a hybrid things like getting more and more. Well, as you can tell, most of the PDE guys nowadays, they are challenged by whether their proposed numerical methods are effective or not. I mean, from the old school. That's why many methods coming from the deep learning, even I'm afraid to file a complaint here. Even they use deep learning without any math at all. Apparently, they work for soliton, okay? Even they can get published in scientific reports or something like journals. Well, where is the theory? Can we have the backbone to support those deep learning really works or not? I hope I just want to play a role here to make a bridge or provide a bridge to linking these two stuff. So that's why I would say, well, it works. Yeah.
So does it apply to all sorts of neural networks? There is something.
Now, of course, it depends on the data structure. It turns out at the end of the day, right? What I proposed at the very beginning of my talk, I already tried to persuade, just like not telling you the Bible, something readings from the Bible. I'm just telling you a philosophy and try to how to formulate the problems, I mean, into our optimal control problems. Yeah.
Thank you, but I was more referring to the basic idea of kind of regarding the neural network as a control system. Like you each layer at time, right? So as time evolves and the layer gets deeper. Like there's something called residual neural network where you skip layers. And I mean, how would that kind of philosophy apply there? You
mean?
There's something called residual neural networks, right? So you kind of rather than doing a
Now, of course, I haven't yet. Well, for the deep learning, I'm understanding right here is a rather naive one. I haven't yet figured out for the CNN or GAN or whether they apply to those kind of framework, and even for some other. Well, you know, every year, every day we have a blah blah neural network, and then right, and whether it would fit for all. Sorry, I'm afraid is really beyond the scope that I can address to you right now. But at least for this kind of very hierarchical, very simple deep learning network, we can see in this way, just like as what Wei Yi told you. And whether it would be effective, of course, it would be a long story, and perhaps we have to spend, hopefully with the help of machine learning, rather than a decade, maybe a few years to getting more message from them. So to this, I should have to apologize. Yeah.
How does it compare to the previous method proposed by Wei Yi?
That's exactly addressed back to her questions. You mean in comparison with what kind of?
In terms of convergence rates.
Well, right here in Wei Yi here, they only got the topological convergence. They don't have a rate. They only showed you the convergence in terms of the Hamiltonian, the gradient of the Hamiltonian. They only show that converge to zero without any rate. There's no rate. There's no rate. There's no rate.
What about your method?
I have the convergence rate. Yeah. Right here. Yeah. Of course, you can choose an epsilon k, but by that time, they only got the topological convergence. Yeah, I mean, just pointwise convergence. Of course, you will say I also got a pointwise convergence here as well, because we have the overall norm of the overall functions, right? But at least we can, well, here is the rate, okay? Epsilon k is something that you can choose. Of course, this epsilon k is your rate, but in return, you have to sacrifice to choose your learning rate, rho k here, being controlled by epsilon k. So more or less, we have to strike for a balance. Yeah.
Okay, so thank you again.
Thank you.